So let's get started with this first question. So we have a Maxwell-Boltzmann distribution. This is for 1 mole of gas. As we know, Maxwell-Boltzmann distribution shows us the distribution of molecular energy. And on the y-axis, it tells us the proportion of molecules with given energy against energy on the x-axis. So the gas can take part in the reaction with activation energy EA as labeled. So what would the effect of increase in temperature? So those are the standard things they like to ask. When you increase in temperature, you will skew the graph to the right, but your activation energy will remain the same. So your activation energy remain the same, but your area under this new part of the graph, the energy of the proportion of molecules with energy greater than or equal to EA would have increased. So you have additional area under the graph that correspond to greater proportion of effective collision because they will have overcome your activation energy. So in terms of peak P, so the peak itself, this is the new peak. It will be lower as you go to higher temperature because the whole thing skew to the right. So it will be lower, and we're looking at more molecules will have overcome the activation energy. That's why you get a greater proportion effective collision. That's why you get a faster rate of reaction. So those are the key ideas that you will have involved in your answer when you tackle a theory level paper. Number 2, you have 4 electronic configurations. 3 of these belong to chlorine, sodium, and vanadium. So chlorine is group 17, sodium is group 1, vanadium is a D block element. So what I mean by D block is they belong to the transition metal series, which are the D block, which are right in the middle of your periodic table. So looking at vanadium should have argon configuration. So after argon, which is 18 electrons, then you will have potassium and calcium. That is your 4s2. Vanadium is group 5, so there will be 3d3. The first D1 will be scandium, titanium is 3d2, vanadium is 3d3. Okay, so we're looking at filling the 4s before the 3d, and the only one that looks sensible there is that they have written it in the form of the argon configuration, written out in full, and then they written the 3d3 before 4s2, but we know we fill 4s before 3d, and that's because you have potassium and calcium before you reach even the 3d. Okay, so that's vanadium. There's vanadium atom. The group 1, there's the S block, and you have 1 element in the S subshell. So there's your third period. There is your third period. The first element in the S block, that is group 1. So there's your sodium. There is your chlorine, which is group 17. Group 17 is in P block. So your P block is the 5th element in the P block. It's still 1 electron short of argon configuration. So that's why it's 1 electron short of the 18 electrons of argon, which means the other element is whatever is shown there, and it's got 4s2 and 3d6. So after potassium and calcium, you fill with 6 more electrons. You are iron. Okay, it's got to be iron, and this is iron atom, right? So they're talking about the atom of another element. Number 3, we have X and Y are in the same group of the periodic table. So as you know, going down the group, first ionization energy will decrease. So down a group, your first IE would decrease. The same thing with your second IE would decrease. So essentially what we can see, if you compare the first, so this is lower than this, compare the second, this is lower than this, this is lower than this, this is lower than this, lower than this, lower than this. So X is below Y in the periodic table. They are in the same group, right? So same group would mean 1 is above, 1 is below. These are lower value. Down the group, first ionization energy will decrease. The same thing happens with second, third, fourth, and etc. etc. And that is due to more filled inner shell. So that means your outer shells become more and more shielded by the inner shell electrons, and therefore they experience weaker attraction to the nucleus, and that's why it's slightly easier to remove. So there's one idea. But then the second bit of the idea is, where is the biggest jump? What group are they in? That's the next question. Going from here is around increase of 800, around increase of 800, around an increase of 1000 something, around an increase of 700. You might thought this is the big increase, but between here and here, I hope you can see these are even bigger. These are around 5000 difference, whereas this one was only 2000 difference. This is the drastic jump. This is the biggest difference. Okay, we said that the biggest difference in the successive means continuously the ionization energy, going from first to second to third, etc., etc. Successive ionization energy, it's between the fifth and the sixth. So that means the 6 electron that you are removing must be from the inner shell, because they are closer to the nucleus, so they are less shielded. That's why it's take a lot more energy, drastic increase in your ionization energy, in your successive ionization energy. So because you are removing the 6th one from the inner shell, so that means we only have 5 outer shell electrons. Therefore, we are looking at group, not the Roman numeral. We use the numerical value, so it's just group 15. So we're looking at group 15, we can cross out selenium and beryllium. Looking at the periodic table, antimony and arsenic. So group 15, you have nitrogen, phosphorus, arsenic, antimony, and bismuth. So what do we say? X is below Y. X is below Y. So this must be X, this must be Y. So Y must be arsenic, X must be antimony. X is below Y. Going down the group, you have more filled inner shells, therefore slightly lower ionization energy. So this is a slightly lower than this for the first ionization energy. X is antimony, and then Y is arsenic. Okay. Number 4. So in China, the concentration of blood glucose is measured in millimole per liter, but in Pakistan is measured in milligram per deciliter. Okay, so L refers to a liter, which is 1 dm cube, whereas a deciliter is 0.1 dm cube. So this is about conversion from millimole to milligram per deciliter. Okay. This is just an information. The real question really is convert this into this. All right. So you're given the molecular formula, which is C6H12O6, because we are converting mole into gram, so we need to relate mass and MR together. So that's why I need to work out the molar mass. That's 12.0 times 6 plus 12 times 1.0 plus 6 times 16.0. Your calculator will show you 1 at 0, but when you think about number of decimal place as per the data given in your periodic table, in a theory paper, number of significant figure matters, just like in practical papers. So we know that mole equal to mass over MR. So if I want to convert mole into milligram, if I want to convert mole into mass, so mass is mole times MR. So that is just rearranging it. I want the mass, so bring that up. So if you follow through the unit, you should be all right. Let's see. 1 liter equal to 1 decimeter cube. 1 deciliter equal to 10 to the minus 1, which is 0.1 dm cube. So I want to convert liter to deciliter. Okay, liter to deciliter. So this, I guess if you look at this is also saying that 10 deciliter equal to 1 dm cube. If you divide this by 10 to the minus 1, then you will get 1. 10 minus 1 over 10 to the power minus 1 give you 1. 1 divided by 10 to the minus 1 give you 10 to the power plus 1. So 1 dm cube equal to 10 deciliter. So therefore, 1 liter is equal to 10 deciliter. So we continue back to the 18.5 millimole over 1 liter. This means per 1 liter. So that means we convert the top bit into mass. So that is millimole. Millimole convert to milligram. So the milli convert to milli. So the mole itself is times 10 to the power minus 3. That is mole. And then I convert it to mass in gram by multiplying by MR, which is 180. 0.1 0.0. However, that will give me the mass. That will give me the mass in gram, because I have converted the millimole into mole. Mole times mR, okay, will give me the mass in gram, but I want the mass in milligram, so I will do times 10 to the power minus 3, because gram to milligram, I divide by 1, gram to milligram. Gram to milligram is times 10 to the plus 3, sorry, big to small, right? 1 gram is 10 to the 3 milligram, so gram convert to milligram times 10 to the 3, and then you divide by, the bottom bit is 1 liter. 1 liter is equal to 10 deciliter from this relationship, so 1 liter is 10 deciliter. So by multiplying this whole thing, I have removed the unit mole. By doing this times 10 to the minus 3, I convert it into mole, I get gram, and then I convert it into milligram by multiplying by 10 to the 3, divide by 1 liter, which is equal to 10 deciliter, so I get milligram per deciliter. So you'll see that the 10 to the minus 3 and 10 to the 3, they both cancel each other out. They give you 10 to the 0, which is 1. Anything to the power of 0 is just 1, as you will have learned from your maths lesson. So that will be milligram per 1 deciliter. So it's just option C there. Alright, so question 5. Each of the 4 species, you isolate it and they are gaseous. Which one is not planar? So BF3 is your case study, where boron is in group 13, so it's got 3 outer shell electrons. Here you form 1, 2, and 3. You form 3 sigma, that is 3 bond pair, and it has used all 3 of its outer shell electrons for bonding. That's why there are no lone pair. Your 3 bond pair repel equally since there are no lone pair repulsion. This is called valence shell electron pair repulsion theory, something you have done in structure and bonding. It's called electron pair repulsion because you've got to talk about bond pair and lone pair. You've also got to explain with no lone pair, your 3 bond pair will repel equally. So you get trigonal planar geometry with 120 degree. So that is planar, trigonal planar actually. So that's not what you want. CH3 plus is a classic carbocation. All carbocations are trigonal planar for the same reason. Your carbon has 4 outer shell electrons, but it has a plus charge, so it no longer has 4, it has lost 1 electron. It lost 1 electron from the outer shell, so now the carbon only has 3 outer shell electrons because there's a plus charge. 3 outer shell electrons, 1, 2, and 3, uses all 3 for forming covalent bond. Again, you have 3 bond pair and 0 lone pair. You have the same scenario as just now. VSEPR tells you that this is trigonal planar again. Alright. Going on to the next one, you have C2H4, which is ethene molecule, which you have done all the way back in GCSE, IGCSE O level. This is a carbon bonded to 1, 2, and 3 other atoms. It's got 1 sigma because this is a double bond. Double bond is 1 sigma and 1 pi. You count the sigma when you want to work out the bond pair for VSEPR. So 1 sigma, 2 sigma, 3 sigma. Around each carbon, you have 3 bond pair. But the carbon obviously form a double bond, which is 1 sigma and 1 pi. So altogether, the carbon with 4 outer shell electrons will have used 1, 2, 3, 4 for bonding. That's why you have normal lone pair or normal electrons on the carbon. 3 bond pair and 0 lone pair, VSEPR, same like that. Trigonal planar on each of the carbon. NH3, however, it's different because it's in group 15. It has got 5 outer shell electrons. It uses 1, 2, and 3 for bonding. It still has 2 electrons left, and because of VSEPR again, your lone pair bond pair would repel more than bond pair. That's why it's no longer flat, because this repel more than that. That's why the shape is trigonal pyramidal with 107 degree as a result of 3 bond pair and 1 lone pair, and this repel more than that, and that explanation is required for electron pair repulsion. Imagine a theory paper, if you don't talk about electron pair repulsion, then this thing is not being used for your shape of molecule argument. That means you are not going to score very well at all. Okay. Argon is a gas used to fill electric light bulbs. We want it to behave the most like an ideal gas, but we think about negligible intermolecular force, they're going to have, in terms of pressure, if you want them to have negligible or minimal or as little as possible, you want them to be as far apart as possible. So you want low pressure. So that means you're not putting pressure on them. You're not squeezing them close together. They are as far apart as possible. In terms of temperature, which is a measure of kinetic energy, the further they can move away from each other, the more negligible the intermolecular force there is, because they can move further and further away. So you want them to have as much kinetic energy as possible. That only happens at high temperature. Okay, so that is when they can be further and further apart. They can exert as little as possible intermolecular force. 7 is an ideal gas calculation question. So we have a volatile liquid. When it goes into the vapor state, at 0 degrees Celsius, it occupies, that is the molar volume at 0 degrees Celsius, which is the same as 273 Kelvin. Alright, but then you form this much volume of the vapor at 100 degrees Celsius and atmospheric pressure. So your pressure is the same, your temperature is different, your volume is different. This is at 0 degrees Celsius, this is at 100 degrees Celsius. Your mass, this is for 1 mole, this is for 0.10 gram, and we want the relative molecular mass of X. If you think about your ideal gas equation, PV equal to nRT, PV equal to mass over mR, RT. So it looks like this question is not an easy just plug it in straight away kind of thing, because we are not given the pressure, we are just told as atmospheric pressure. So the pressure here and here are the same. If I think about just from this information alone, what is the pressure? It's going to be nRT over V, where if I have the N, which is 1 mole, I have the R, and then the temperature is 273 Kelvin. And if I do the volume in dm cube, so obviously you can convert, you should convert the volume, because the volume here is in meter cube. If I leave this in dm cube, because I'm going to use it directly, put it into here, where my actual volume here is also in dm cube, so I know the conversion factor will cancel out. So essentially I'm doing a ratio. Alright, if you think about it, I'm doing a ratio. So now I sub into this equation. So this is the pressure from here, it's the same pressure there, so I can sub it in into our scenario here, where we are given 0.10 gram of that volatile liquid X, and we are supposed to find out the MR. Alright, so the MR for this non-volatile liquid X is going to be MRT over PV. Your MR is going to be 0.10 gram multiplied by R multiplied by 100 degrees Celsius to Kelvin is 100 plus 273, so that's 373 Kelvin. My pressure is supposed to be this, so I just sub it in, 1 times R times 273 over 22.4. I make note that I did not convert it to meter cube, but I also multiply by the volume, which is this. I would leave it in dm cube because I can see the unit cancel out. If I convert this to meter cube, then the unit will also cancel out. The conversion factor will also cancel out. But because I could see the volume there being dm cube, essentially I'm doing a ratio. So I sub in the atmospheric pressure with the volume in dm cube. As you could see, the volume in dm cube actually get cancelled out, as would your conversion factor if you had done a conversion factor. Your R divided by R would also cancel out, and then nothing else will cancel out. If you rearrange that equation, you should be able to see that there is times 22.4 divided by 273 times 0.025, and that comes to 0.10 times 373 times 22.4 divided by 0.025 times 273. So it's a ratio of the temperature, it's a ratio of the volume. Okay, in order to work out the MR, all I've done instead of doing the ratio method is I have made this into a subject of formula and I sub it in. You could also do this via the ratio method, where you could see that cancelling out much easier. Alright, so both methods will have been equally acceptable, especially if we talk in mathematical terms. Make one into the subject, substitute into the other. It's similar to taking ratio of both things, as you would have known when you solve for equations in mathematics. Question 8 is about complete combustion of propane 1O. So propane 1O is as shown here. You are given enthalpy of formation. So we know that the sum of the enthalpy of formation of products minus the sum of the enthalpy of formation of reactants is equal to enthalpy change of reaction, especially when you are given enthalpy of formation. Remember, the enthalpy of formation is defined for forming 1 mole of the substance. Here you're forming 3 mole of it, so you need to multiply the CO2 formation by 3. So there's 3 times minus 394. Use bracket, and you have 4 of water. Close bracket, and then for your reactant, you have enthalpy of formation for this, but not for this because this is an element. When you think about your definition of enthalpy of formation, forming 1 mole of the substance from its element. Okay, so forming an element from its element is always going to involve 0 enthalpy change, provided they are in the standard state, right? Which they are, because that's part of the definitions of standard enthalpy change of formation. Okay, so there's just 1 mole of the propane 1O. So if you do that correctly, so they don't really want the value, they want the expression. So there's 3 times minus 394. 3 times minus 394, what am I looking at? Have I done this wrong? Formation of product minus the formation of reactants. Okay, what have I done? So I can see that the 394 here hasn't been multiplied by 3, so this is incorrect. The 394 here hasn't been multiplied by 3, that is incorrect. The 394 here is minus overall is minus 394 times 3. Here is a plus, and that is incorrect. Here is a minus overall, is minus, so they move the minus out. You get 3 times 394, and you get minus, they bring out again 4 times 286. The minus and minus they bring out, they become plus 303. So we're left with B. This is quite a confusing expression. Personally, I would have left it here, but I would have used bracket, as is the case with any bookkeeping. Okay, any good bookkeeping would tell you that you should use bracket and do them step by step, right?